This video discusses how we're actually going to use HEC-RAS to simulate a riffle, run, pool, glide sequence. A rectangular channel with a bottom width of 33 feet and a HEC-RAS height of 10 feet carries a flow rate of 300 cubic feet per second. The roughness coefficient is 0.0542. The overall length of the riffle, run, pool, glide sequence is 140 feet. Each facet has the following percentages of the overall length and the associated bottom slopes. So the riffle comprises 20% and it has a bottom slope of 0.015. The run is 30% and has a bottom slope of 0.021. The pool comprises 25% and it has a slope of negative 0.0006. The glide has a composition of 25% and has a bottom slope of negative 0.0126. If we look at the overall sequence, it has the average bottom slope of 0.006. Notice these numbers of the 33 feet and the roughness coefficient and the 300 cubic feet per second are from the previous riffle design example. What we're going to do now is use the HEC program to simulate the flow through the rectangular channel. So we're going to assume that this natural channel is rectangular just for the sake of computation. So within the HEC-RAS program, we're going to use the default coefficients for the losses related to contraction and expansion. So K sub C will be equal to 0.1 and K sub B will equal to 0.3. We're going to create 10 rectangular cross sections with the most downstream cross section being the downstream end of a riffle. And the cross sections will be numbered from 10 to 100 in steps of 10. The bottom width of the rectangular channel should be equal to the bankful top width of the previously designed riffle. So in this case, we're going to use the top width of 33 feet to be the width of the rectangular channel. The boundary condition at the downstream end will be a known water surface, which is initially unknown. And I know that seems like kind of a conflict, but we're going to have to iterate to determine what the correct water surface is at the downstream end. Next, we're going to select the known water surface elevation at the downstream end, run the simulation, and examine the water surface elevation at section 90. That'll be in the same position, just 2 cycles upstream. When the downstream depth at section 10 matches the depth at section 90, the solution is achieved. So in order to do this, a spreadsheet was built which takes the length and bottom slopes of each facet and determines the elevation adjustment which is necessary in HEC-RAS to correctly define the channel bottom. You can then take the cross sections, which are, the elevation adjustments, which are shown in the spreadsheet, and you can import them directly into HEC-RAS to simply enter the cross sections. So the next video will discuss the spreadsheet.